everybody. This is Javier Gorroño from Universidad Politécnica of Valencia, and I'm coming here to give you a short talk about the potential of Sentinel-2, Copernicus Sentinel-2 mission, to monitor methane point emissions, to actually map the emissions from, let's say, oil and gas or other sites. I will go into a bit the details of the methodology, the sites, and so on, and then I will end up with some examples and a very short example that you can do with the Copernicus browser. Very simple, but I think it shows the potential and the easy way to detect these emissions with these platforms, cloud platforms. So let me see. Okay, now it works. Okay, so what's methane mapping from space? So in the last few years, we've got several missions that are able to actually map at a high resolution, high spatial resolution, the plumes from space. We are talking about hyperspectral missions mostly. These are like ENMAP, EMIT, PRISMA, Chinese mission like GAOFEN, and others, but they are usually in the 30-60 meters resolution, and they have a medium sensitivity. They can have a wide spatial coverage, and you can detect from 100 kilograms hour onwards emissions. So you see here that they cover basically the whole shortwave infrared, where you've got the methane transmittance, especially you've got a really strong peak in the 2300 nanometer region. But on the other side, you've got multispectral missions. These multispectral missions are not so sensitive. They have a low sensitivity, but they have 20-30 meter resolution, and they can monitor with frequent and global coverage like Sentinel-2 and Landsat. And you can see here in the image where the Sentinel-2 and Landsat bands are in the area of the 2200, where you can find the methane absorption. On the other hand, you've got also a sensor like WorldView 3 with 3.5 meter observations, a better capacity to detect methane, but this is under payment, so they are not open for everybody. So methane mapping from space, we've got different targets. We are starting with onshore oil and gas facilities. We move into offshore oil and gas facilities, and now we are also moving into landfills. We've got examples like, for example, even the palm oil mills have been monitored for methane. And in the end, we are expanding these sites. We are moving into different areas. And this is a whole monitoring strategy that is, it includes the combination of different things. This methane mapping from space combines with inventories to reconcile inventories with methane mapping from space. They also bring auxiliary products, databases like flaring data, which is connected to methane. It's actually methane being burned. And we've got also organizations like UNEP IMEO, who is working into bringing this at a sort of operational level and trying to connect all this with political action. So going into why Sentinel-2 mission is capable of detecting methane, we've got basically two bands in the shortwave infrared, which are the band 11 and the band 12 that you can see here in the image, that respond very well to methane absorption, especially the band 12 is in an area where you've got methane absorption, whereas the band 11 has almost no methane absorption. It's got, as I was saying before, it got a very good advantage. One, the obvious, it's open. It's got a 5-day revisit, and it's got 20 meter spatial resolution. So those are very good points. The disadvantage is obvious that it's got limited sensitivity because it's not designed for this. It's got a broadband, the band 12, and obviously it doesn't respond as well as a hyperspectral mission. And usually detections, you need to be at the 1.5 or 2 tons per hour in order to start to see results. So there's a whole methane retrieval methodology that briefly I described here with this graph. I show you here, where you start with a methane concentration map that you obtain from the retrieval of the radiance bands. Then you can threshold, or you can filter out the whole number of outliers that you can find in the image, and you can create a manual or semi-automatic plume mask that can be done with, as I say, manually, or you can use a machine learning process There are several methods to do this. And then in the end, you've got a final plume mask, which you can use to actually quantify the amount of methane that is released per hour, which is the quantity that is of interest to actually understand the amount in kilograms that is released. So the methane enhancement is retrieved as a simple plots of a temporal and band ratio of the band 12 and band 11 that you've got here in the equation. We approximate this as the transmittance of the plume, and based on a relationship between the transmittance of the plume and the amount of methane, we can establish that value. This relationship can be based on here, for example, in the equation, it can be based on a simple Beer-Lambert law, or for example, in our case, we relate this with a lookup table based on relative transfer equations. So going into this ratio of bands, which is very straightforward for Sentinel-2. Other methodologies look for example, at a match filter when you've got many bands in the hyperspectral, but for Sentinel-2, because you've got only 2 bands, this is very straightforward. So you just use the ratio of the 2 bands. So basically your target band is the band 12, which is the one that detects the methane, and your reference band is the actual band 12 without that methane, the band you are going to predict. So the simple case would be to actually bring this band 12 divided by band 11. And here you've got the panels A and D, where you see the result you've got with this approach. You can see a bit in the center the emission, but not so clear. And it's as soon as we start to bring this reference of radiance reference that is not just band 11, but is a band 12, let's say, from a close date or several date, and we normalize by that, assuming always that the plumes are changing with the wind direction and are not overlaying temporally. So you can find much better results like the panels E, especially F, that you can find here. And this is a bit the whole idea, is to play with a normalization of the band 12 with the closest you've got without methane. So the idea is very simple, and you get an enhancement image. The thing is that from that enhancement image, we've got a detection, which, as I was saying before, can be based on a threshold or on automatic methods. For example, for UNEP IMEO, they have developed here in this example a whole algorithm that is based on machine learning and can automatically infer where you have the plume with quite a good successful results, because let's say manually is very, very difficult. We in the beginning, let's say we used to do that, but it came to a point where you've got hundreds or even thousands of plumes, and it's almost impossible. And then from the quantification level, we've got a quantification that actually takes this mask and converts into kilograms hours, which is the quantity we are looking for, and estimates how much methane is being released per hour. This quantification is based on transport simulation and is validated against in situ control relays. When I say in situ control relays, it's basically you go into a place with a big truck and you know exactly what you are releasing, and that's how we validate that what we are actually measuring. They don't tell us exactly what they are measuring and what they are releasing, and we just here you've got an example of the validation we carry out with the guys from Stanford, and the results were quite successful for these initial algorithms. And yeah, so let's say few examples with Sentinel-2. So as I was saying, with Sentinel-2 might not be the best sensitivity for a mission, but the thing is, because it's there, it's 5-day revisit. It brings a lot of opportunities, and here you can see different examples like this. The one on the left is a plume in Corpege, which is Turkmenistan, that you can see from an oil and gas rig. This other in the center is an example in Hassi Messoud, which is in Algeria. It's another place we are monitoring. And the one on the right is a plume that we can find, for example, in the Permian Basin, which is an oil facilities in the US. So said is that if you go, for example, to this web page called methandata.unep.org, you will find over 10,000 or more at the moment of detections with different satellites that they are continuously monitoring. Among them, many of them are with Sentinel-2. And what you will find is that they are monitoring absolutely everything, and it's expanding and expanding, and the capabilities are enormous. So said this, after all this basic introduction of the thing, I just wanted to show you that it's not so complex, and we are basically trying to do this with the help of these cloud platforms, because they are helping us a lot to automatize the process. So I just wanted you to, it's very simple, okay? But I just wanted to show you a very quick test. So if you want to do it by yourself, it's also possible. You can take a screenshot and try by yourself. We can make a quick test in the Copernicus data browser. I didn't do it in WEkEO because at the moment it's not possible to do a ratio of 1 directly, but I've been told that this will be possible in the near time, in the short time. So if you go to this center, like 38 north, 54 east, you can find an image like the one I'm showing you here, and you will be somewhere in Turkmenistan. You can select the Sentinel-2 Level 1C and press Show Latest Date. You can select a layer, which in this case will be a custom layer. You can create an index with the band 12 and the band 11, as you can see here, just dragging the band 12 and the band 11. And you can create a time lapse by pressing the icon you've got here on the right of the screen. So if you want to do it by yourself, as I said, you can take a screenshot and try by yourself. But here I've got the example just to show you that it's straightforward with this. And you should see something like this. If you see the image, this is a GIF of different days. What you must see in the center of the image is a plume that is actually coming out of an oil rig. I don't know if you appreciate here in the middle of it, and it's changing with the different wind through different days. So basically, this is done through the browser very quickly, but we've got the same. We are doing the same with the APIs, Python APIs that you can find on WEkEO, and it's very easy to implement at the detection level. Then we can quantify, but obviously for us at an operational level, it's very easy to have access to all these data sets online. And from this talk, I can say that as a summary, so methane mapping from space has been shown to be very useful to monitor and mitigate emissions, to actually bring all this satellite data into real action. We have seen that. We have seen the whole process in really few years. Sentinel-2 mission contains sensitive bands, and as I said, it's not the most sensitive mission, but it's playing a very important role in the development of a global monitoring strategy, because as soon as you've got an event, let's put an example. You've got a gasoduct that is broken, a pipe is broken somewhere. Is always Sentinel-2 is open and is there. Sentinel-2 and Landsat are there. So it's the first one that is always going to be there to monitor. So that's why it's so useful, because it's open and it's so easy, as I told you here, with a very simple example, you can go and monitor in a minute. So we can see that there is a retrieval method for Sentinel-2 based on a temporal band ratio of band 12 and band 11, so that the quantification can be based on a transport simulation and validated against in situ control releases. And importantly, as I said, you've got all these online platforms such as WEkEO, which are facilitating a lot the implementation of this at an operational level. And that's all.
Thanks a lot, Javier, for your presentation. And we have a few questions for you, obviously, and we will go to that part. So I will wait till it's on the screen. So the first question being, how does spatial resolution of Sentinel-2 impact the accuracy of methane hotspot detection?
Yeah, I mean, the accuracy of methane hotspot detection, I mean, the sense, we call it sometimes the probability of detection or detection limit, it is typically a combination of the spatial resolution and the SNR. So the SNR of Sentinel-2 is acceptable, let's say. So you've got this problem, especially you've got two problems. Or challenges, let's call it that way. That one is that the SNR is not massively good, and especially the heterogeneity. So you can find many outliers because you are making a ratio of two bands. When you are using a whole hyperspectral, you can find less outliers, so it's much better and much easier to detect. But in general, very simple is the spatial resolution, the lower the better, combined with the SNR, the higher the better. Plus, the more bands, the better. It's a play of a game of thought.
Okay, thanks for the explanation. Okay. Sorry. What is the evolution of methane emission over time in the last 10 years? Did the sources vary?
Well, that is something I do not exactly. I've seen. Well, you can find the evolution at an absolute level of the methane, and it's always continuously rising. I think now it's 1900 parts per billion, so going from 17, 1800 parts per billion. Then there was sort of a hiatus like 10, 20 years ago, and then it ramped up again. There are many discussions about these sources, and at the moment, what I can say that with methane mapping, we are trying to find out the sources which are more concentrated. We have started with oil rigs because they are a whole source coming out from a very hole, let's say a very tiny hole. So we've got everything concentrated. We are moving into landfills which are less concentrated, and we can move also now in. We also recently moved into palm oil that you can also find, but it's more difficult because the less concentrated they are, the more difficult it is to detect from a satellite. For example, the rice, which is one of them. So there are a lot of potential emissions, and the sources vary a lot. And there are even natural emissions like the one from termites, which are very well known, and wetlands, and so yeah, there are many sources.
Okay, thanks. The next question, does the plume detection algorithm yield any false positives?
Well, yes, it depends on the plume detection algorithm you are using, and it depends on what methodology you use. So, for example, what we are trying to do is, depending on the mission, you've got a lot of outliers, we call them. So in the image I was showing you before, you can find a plume, but you can find other things that are shown as plumes that they should not be a plume. Let's say, for example, a solar panel typically shows as a false positive. The thing is that we've got different strategies. So at the moment, for example, I would say that the best strategy is to use a machine learning, being very cautious, so it doesn't detect absolutely everything. It tries to detect the things, and then there is a human control over those. Like, for example, you need to make sure that the plume is going in the same direction as the wind, that is have this sort of expected plume shape and so on. So there are many things there. And yes, still you can find false positives, of course, but they are rare after you have all these steps.
Okay, it's clear. Thanks. Next question, still about the plume. How are the limits of the plume decided in order to mask it properly?
So it is not a single rule, but let's say if we can put a rule of the thumb, is anything that is above 2 sigma of the noise of the enhancement of methane. You obtain let's say the most straightforward way is you get the image of methane enhancement, you assume a sparsity, therefore you calculate the standard deviation of that image, and over 2 sigma, you will say that this is what you are going to mask. That would be the straightforward way. But obviously, it's not so straightforward, so you can do it manually, and you can do, for example, if it's a machine learning algorithm, you can do with different other strategies. But the most important, I would say, is that whatever the method you mask, you calibrate. Let's say the same, you calibrate your flux rates with the same mask methodology that you are going to use in your operational case. So that would be the main ideas.
Okay, thanks. Another question. So I've read that Sentinel-2 with B11 and B12 isn't really suitable for methane detection. Maybe Sentinel-5P are better for that.
Yes, so well, there is no better or worse. As I was saying before, there are different possibilities. What you've got with Sentinel-5P, we use what is called a tier like layers. So you start, the way we detect things is like you start with Sentinel-5P tropomic, which goes into hotspots. Then you can move down to other missions, like let's say Sentinel-2, Landsat, and so on, and you can go down to another layer of, let's say, Mmap or so. And the different layers bring you different temporal revisits, bring you different spatial resolutions. So Sentinel-5P, for example, is much better in terms of, has almost daily coverage, has a very good spectral sampling at the 0.1, 0.2 nanometers or so in that area, which brings very good retrieval of the methane, but it's very difficult to be used for let's say for methane plumes, because they are at the scale of, let's say, hundreds of meters at the most, or 1 kilometer, whereas the Sentinel-5 pixel is, I think, is at the 8 kilometer or so. So what you find out is that it's not very sensitive to these methane emissions. So it's much better used for methane area mapping. So understanding the thing at the absolute level, whereas this Sentinel-2 and these other missions are much better at the relative level.
Okay, thanks for the explanation. The next question and the one after that are kind of the same. How scalable is this method to detect carbon emissions plumes? And also, has this been used for other purposes to track methane, like agriculture or farming? So, is there another use of the...
So do they mean CO2 emissions or?
Yeah, I guess so, yeah.
So basically, we already do that. So we detect both plumes of methane and CO2 and also NO2. So this is happening. So it's actually with Sentinel-2, there's been a publication where it is possible to detect NO2. Again, not a very sensitive values, but they've been doing through power plants, for example, where you can monitor the NO2 emissions of power plants, large power plants. And for CO2, for example, we work on those kind of detections where it's very important, for example, the co-detection of CO2 and methane in flaring systems, because the flaring basically tries to burn the methane that is in excess, or they don't want to sell it. And we can convert that CO2 on the potential methane that is burned. And there is a part which is burned. There's another part which is not burned. So you've got methane and CO2 co-emitting. So yeah, let's say methane, CO2, and NO2 are something that is already happening.
Okay, thanks. Okay. And yeah, so does this method detect methane emissions over ocean?
Yeah. Actually, I would say we were the first ones to do that with a satellite over the ocean. It was in an oil rig in Mexico, which we found out with Volview 3. And the difference between the ocean and the land is that basically in the ocean you've got a surface which is very dark, and the best way to find out is trying to go into mirror-like, into, let's say, the mirror, how do you call it? Sorry, I forgot the name. So basically in mirror configuration where you will find the glint, sorry, the sun glint. I couldn't find the word. So if you go into the sun glint configuration, you will find a lot of radiance, and that's where you will be revealing the methane. But it's very important also to monitor the methane emissions over the ocean, because many of these oil facilities are completely non-tracked. You cannot go there, and yeah, they are even more how to say, unmonitored.
Okay. Well, thanks a lot for the presentation and the questions. We will have to stop there for the time we have. But yeah, thanks again for your participation and enjoy.